So in our last lecture, we talked about the Bernoulli's law and just conceptually what it says. So what does Bernoulli's law tell us? Faster moving fluids exert less pressure. And the number one example of that is an airplane wing. So what we did is we looked at, I think this is pretty much where the lecture ended. So airplane wings are shaped like this. Here's the wing. And so when air hits the wing, some of the air goes across the bottom, some of the air goes across the top. Which path must be faster? The top, because it's going a farther distance in the same time. So we have fast on top, slow on the bottom. Bernoulli's law says faster moving fluids exert less pressure, so we get low pressure on top of the wing, high pressure on the bottom of the wing, and that creates lift force. So what we're going to talk about today is the Bernoulli equation, which is the longest equation of the entire year. So here we have the Bernoulli equation. It's not as bad as it seems because the left side, because remember you have to have, for the AP exam in May, you have to have all the equations memorized for the multiple choice. So this is the toughest one, but it's really not too bad because if you look at it, the left side of the equation and the right side of the equation are the same. Just change the ones to twos. Okay, so a couple things. When you're using the Bernoulli equation, so P is what? Pressure. You have to be, can anybody tell me what unit? What's the metric unit for pressure? Pascals. Not kilopascals, pascals. Density, D is density, has to be in kilograms per cubic meter. Velocity in meter per second, so D is density. Gravity, 9.8 meter per second squared. Okay. The key thing here is you have to be in pascals. Hey man, look up here. The most common conversion, the one that you should have memorized, if they give you pressure in atmosphere, you should know that 1 atmosphere, which is the pressure you're feeling just sitting in this room right now, the pressure of the atmosphere, 1 ATM is equivalent to 101,300 pascals. That's a very common conversion. Okay? So, I want to start by talking about H. So see in this equation here how we have these H's, H1, H2. The only time you're going to have to factor in DGH is when there's some sort of vertical climb. Like here, if you have a pipe that goes up a hill, what you're going to do is you're going to set the lower level. Remember when we did potential energy? All the H's got measured off the 0 point. So what you'd want to do for a situation like this is call this level down here, call this H1, set it equal to what? 0. So boom, H1, 0. And then H2 would be up here, where H2 is this vertical height right there, right? That'd be H2. So for a situation like this, what's going to happen to both of the H's? Yeah, they go away, because look, you just draw a line through the middle, that's your 0 point. This right here is H equals 0, so H1 would be 0, and H2 would be 0. That make sense? So the only time you have to factor in the DGH is when there's some sort of vertical climb of the pipe. All right. Now, ignoring the DGH, I want to focus on this situation right here, just so you understand what Bernoulli's equation is all about. So ignoring the DGH, we have this part of the equation equals that part of the equation. So look, on Friday last week, we talked about how when you have a fluid moving through a closed pipe, if the fluid goes from a fat area to a skinny area, what happens to the fluid speed? As the fluid moves from the fat part to the skinny part, what happens to the fluid speed? It increases, right? So here we have V2, and over here we have V1. So V2 is larger than V1, right? So put arrow up for larger, arrow down for smaller. The D's are the same. The D's are a constant. So look, just looking at this equation, if V2 is big, what must be true about pressure 2? It must be small in order for these two boxes to be equal. You guys follow that? And over here, velocity 1 is small, which means pressure 1 must be bigger, right? Faster moving fluids exert less pressure. As this velocity gets bigger, what happens to the pressure? It gets smaller. That make sense? Okay. So for the most part, guys, the Bernoulli equation, as big and scary as it looks, it really turns into plug and chug. It's going to be like, so if the pipe is totally horizontal, you're going to be like, bye-bye H's, cross the H's out, right? DGH goes away. And then you'd be like, okay, we got this velocity, we got V1, we got V2. Okay, we got P1, and then, you're solving for P2. It's going to be plug and chug where you're missing one variable, right? But there are two super important things that I have to show you, and you got to pay attention, because if you don't know these two things, you're going to be stuck. All right, so the two things that you have to know are this. So number one, pressure on a fluid open to the atmosphere is 1 atm, which is 101,300 pascals. So here's an example. So I have this diagram. This is actually from a homework problem, this diagram here. So looking at this fluid, there's two regions. We have region 1, which is the fat part, region 1, and region 2. Which of those two regions is open to the atmosphere? Region 2. If you look at this pipe right here, this is totally open to the atmosphere. So what is that telling us? And the problem's not going to tell you this. The problem's not going to say, oh, and notice that region 2 is open to the atmosphere. They're not going to tell you that. They just expect you to know it. So what would be the pressure of the fluid in that region? 1 atm, which is 101,300 pascals. Make sense? Now what would be the pressure in region 1? It's going to be something greater. So if somebody's pushing on this plunger right here, if somebody comes along and exerts a force on the plunger, that's going to shove the fluid through. The pressure in region 1 is going to be greater than 1 atmosphere. Does that make sense? It's not open to the atmosphere. Got it? Okay, so that's number 1. Fluids open to the atmosphere, the pressure on that fluid is equal to 1 atmosphere. 101,300 pascals. Okay, number 2 on the list. And if one velocity is huge and the other velocity very small, set the smaller velocity equal to 0. So again, here's a good example of that. So we have two regions. So we have this is region 2, this is region 1. Which velocity is going to be dramatically larger? So we have velocity 1, that's the velocity of the fluid in region 1, and then we have velocity 2, which is the velocity in region 2. Which of those two velocities is going to be way bigger? Region 2. The fluid's going a lot faster. Now guys, look at the Bernoulli equation. What do you notice about the velocities? They're squared. So if you have two values that are already significantly different, what happens if you square those values? The difference becomes even farther apart. So a very common thing with the Bernoulli equation is you take the slower velocity and you just set it to 0. Okay? That make sense? Is the problem going to tell you to do that? No. But it's the only way. You're going to reach a point where you're like, I have too many unknowns. So then you look at it and you go, oh yeah, that fluid speed is way smaller than that fluid speed. Set the smaller fluid speed to 0. Yo.
What do you mean by way smaller?
Well, like a syringe going into a needle. So you got the fat part of the syringe, tiny part of a needle. The next screen will also be a good example of that. Okay. Okay, so here's what we're going to do. Now this problem, the old hole in the side of the tank problem, the College Board is obsessed with this. They put this on the free response a lot. You know, there's 7 free response questions on the AP exam. The College Board loves this problem. And if you know how to do it, you're all set. Okay, so here's what you got. Fluid comes shooting out of the side of this tank, okay, with some velocity v, okay, which we can solve for. The fluid goes 0.6 meters horizontally and 1 meter vertically. What they want you to figure out, just with this given info, this is all you know. The only thing you know is the horizontal distance, the vertical distance. What they want you to solve for is how deep must the water be in this tank. Now, looking at this problem, this is going to pull from a previous chapter. What topic does this problem pull from? Two-dimensional motion, projectile motion. You know, this is the same thing, same exact thing as if you had a ball rolling off a table. If a ball went off a table, that's 1 meter here, 1 meter. The ball goes, lands over here, 0.6 meters. Could you figure out the velocity of that ball? Yeah, this is projectile motion. So you have to use your knowledge of projectile motion to figure out this velocity, okay? Once you know that velocity, you can use the Bernoulli equation to figure out what this h must be. Are you going to use the 2 key things I just went over? Yeah, so for example, what's the pressure on the fluid as it comes out of that hole? 1 atm, which if you actually plugged that in over here, you'd want to make sure it's in pascals. You have to be in pascals. But we'll just say 1 atm. What's the pressure on the fluid up here? 1 atm, right? Look, so the pressures are going to cancel. The pressures are going to cancel out here. Look, I've discovered over the years a way to help kids get their brain around this problem. Think about this tank. Instead of it being a tank, think of it like this. Think of it being like a syringe that got bent. So it's like a bent syringe. Okay, and then the water's up here like this. You got water shooting out like that. Okay, so this velocity here is that velocity there. So we got 2 regions. I would call this region 1. Down here is region 1. Up here is region 2. So H1, what do we set H1 equal to? 0. And then go doot, 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 doot. Up here is going to be H2, which is going to be this vertical height right here. Right? So just think of it like a syringe that got bent. You know what I'm saying? The hole in the side of the tank. What's the pressure on the fluid down here in region 1? Pressure 1 is going to be what? 1 atm. Up here, region 2. What's the pressure on region 2? 1 atm, because they're both open to the atmosphere. So what's going to happen to these pressures? They cancel out. Okay? Now, V2, I don't want to do the whole problem for you yet. V2, and then this would be V1, right? So this water is kind of dropping down through the tank, right? With some velocity. The water level's coming down. So we got 2 velocities here. We have the velocity of the fluid shooting out of the hole, which is V1, and then we got the velocity of this water level coming down, which is V2. Which of those 2 velocities is dramatically smaller? Smaller. V2. So you go later V2, bam, cross that out. Okay? And then what was H1? H1 we said was what? 0. That's our 0 point. So you're left with this equals this. I've done like 90% of the problem for you. So try it from here. You're solving for how deep the water in the tank must be. The answer comes out as 0.09 meters. So take like, 5 minutes, and what's the main thing you got to do? The main thing you got to do is use projectile motion and calculate what this velocity is here. using the horizontal displacement and the vertical displacement. I'm going to kind of walk you through it all again. So look, the velocity of the fluid coming out of this hole, we can find this using projectile motion, which I'm not going to go over that. Oh, let me turn the screen on. Here, the screen was off. So we can find this velocity using projectile motion, which I won't go over because I don't want to make this video super long. If you do it correctly, though, your answer will be 1.328 meter per second. Okay, that's just kinematics. We got that from kinematics. Same thing as a ball. Same thing as a ball rolling off a table that's 1 meter high and it lands 0.6 meters away. You know, projectile motion. Okay, so what they want us to find is how deep the water is in this tank. So let's define this level right here as being H1. So what should we say that is? 0. So this right here goes away. H1 goes away. So then up here will be H2. And that's what we're solving for, right? It's that vertical height right here. We're looking for H2. So what is this velocity here? This velocity right here, is it V1 or V2? It's V1. It's the velocity at level 1. This level right here is level 1. Again, a great way to think about this, think about it like this. You got a syringe that's been bent, and then the water's kind of coming out of this hole here, like this. So down here is level 1, H1, which means this right here is V1. Okay, so what's V2? V2 is the velocity of this fluid coming down, right? Like the water, if there's a hole in the side of the tank, this water level here is going to be dropping, correct? And that's a velocity. You know, how quickly that water level drops, it's a velocity. So which of these two velocities is way smaller? V2. So take V2, cross it out to 0. Now, notice that this hole right here is open to the atmosphere. So what's going to be pressure 1? 1 atm, which if you actually plugged that into the equation, you'd want to convert it to pascals. Okay, what's pressure 2 up here at the top of the tank? Is the top of the tank open to the atmosphere? Yep, so what's the pressure up there? 1 atm. So the point being, this pressure and that pressure are the same. So what happens to them? They cancel out. P1 and P2 are the same, so they drop out. And what we're left with is 1/2 dV1 squared equals dGH2, right? That equals that. The densities cancel, and now we can solve for H2. So H2 is going to be V1 squared over 2G, 1.328 meter per second squared over 2 times 9.8. So this comes out as 0.09 meters. Okay. Hey, and I want to show you something. Look at, does this at all look familiar to you? It should look somewhat familiar. It's basically potential energy and kinetic energy, right? It's almost like this. It's almost like you had a ball on top of this hill, right? The ball rolls down the hill and leaves with some velocity, right? What type of energy does the ball start with? Potential. And it ends with what? Kinetic, 1/2 mv squared. So look at mgh equals 1/2 mv squared. It's like this. So instead of mgh, it's dgh equals 1/2 d. You know, just change the d, just change the m to d. So it's very similar. It's like conservation of energy for fluids.